Hello and welcome to lecture 8 of computational complexity. So in the previous lecture we started seeing the proof of Cook-Levin theorem, right? So the goal is to show that SAT is NP complete, and first part was showing that SAT is in NP, which we had already seen. Second part, which is the main part of the proof, is to show that SAT is NP hard. That is, all the languages in NP can be reduced to SAT. Right, so we took an arbitrary language A and then we are attempting to show that A reduces to SAT, which means given an instance W of A, we need to produce a SAT instance which will be a Boolean formula such that W is in A if and only if the Boolean formula, which we will call f of W, is satisfiable, right? So the main idea was to create this computation table of W. So W, since A is assumed to be in NP, there is an NP machine that decides A, and you write down the computation table of that NP machine, and we will create an equivalent formula, a Boolean formula, such that the Boolean formula will encode the machine performing a sequence of computations and going to the accepting state. So if there is a possibility of W getting accepted, the Boolean formula will have a satisfying assignment. If there is no way of W getting accepted, then the Boolean formula will not have a satisfying assignment. So that is the high level idea. So there are the formula that we created is called, we call it phi. There are 4 parts to phi: phi start, phi move, phi accept, and phi cell. Phi cell just checks the encoding, right? So we construct phi with the help of Boolean variables of the form x, I, j, k, where I and j are some integer from 1 to n power k, denoting the row and column of the computation table, and k is a member of the alphabet delta, which can be either the state or the tape alphabet or hash, right? One of these three. So an xijk denotes whether the ijth cell contains the symbol k. It will be set to true if the ijth cell contains the symbol k, and it will be set to false if ijth cell does not contain the symbol k. And the phi cell is trying to measure, check whether this the true false assignment is a valid setting of exactly one entry per cell. Phi start is checking whether the starting row is a valid starting configuration of the Turing machine n on W, the input. Phi accept just checks whether there is an accept state anywhere in the computation table. And where we stopped is phi move, which is a formula where we had to check whether the entire sequence of moves is valid. So given each row, does each row is a configuration. So does the second row correspond to a valid move from the first row? Does the third row correspond to a valid move from the second row, right? And so we have rows after rows. So one may think that we need to check the entire row or entire pairs of row, right? So we want to check whether second row follows the first row legally, and third row follows the second row legally, and fourth row follows the third row legally, right? So you may think that you may have to check construct a Boolean formula that involves the entire row followed by the next row, but we don't need to check such a big set of entries. It is enough to check 6 entries at a time, right? So here I have marked it in red. So what we will do is our checking will be broken down into windows like this, which is like 2 by 3 windows. That is the windows that have 2 rows and 3 columns. So the thing is that given 2 rows, right, as I have drawn in the picture over here. Now we can tile the entire, or we can cover the entire 2 rows by having 2 by 3 windows like this. So first we started at the leftmost, then shift by 1, then shift by 1 more, and so on. So the entire class of the entire two rows will be covered by a shifted so and so on. So finally we will have something here as well for the last the last columns, right? And for everything, like, right? So it is enough to check that each of these 2 by 3 windows is a valid 2 by 3 window. So what do I mean by valid 2 by 3 window? A valid 2 by 3 window is any set of windows that can occur in a computation, in a valid computation. So for instance, if you just have a look here, what are the values that occur here, right? So for instance, if you look here, let's say W3 and W4 are there in the top row, same in the second row, and this window, right, it contains the same entries in the top as well as bottom. So any window that contains the same entry in the top and bottom is a valid window, right? And if you look at let's say this one, maybe I'll just this one that I'm marking by light blue, right? So here the entries are not the same. So in fact all the top 3 entries are, or bottom 3 entries are different from the top 3 entries, but this is also a sequence of a valid computation, right? So in the previous lecture we saw how a move can result here, right? So anything that is possible to occur as a result of a valid transition of the Turing machine, that is considered as a valid window, right? Any 2 by 3 thing that can occur, right? So this occurs because upon reading W1 from the state Q, the Q start, it can write A in place of W1 and then move to Q8 and then move right. So sorry, I earlier mentioned that all the 3 entries are different. All the 3 entries are not different. So W2 is the same, the rightmost entry is the same, right? But we could have all the 3 entries different. Again, this example does not show that, but we could have that. So maybe what we will do now is to see some examples of some valid windows, right? So let's see some examples. All right. Let's say the top row has BQA, okay, and let's say the transition function had, so this means that the tape head is reading A and the state is Q. Now suppose in this situation the machine writes R, moves to the state D and then moves right, which means this B will remain as it is. The A is replaced by, so sorry, this is wrong, just 1 second. So I think there is a small issue here in my previous lecture. So I have inverted the order of the state and the symbol that is read or written. So but you may just ignore that, just follow what I'm about to do. So this means that it reads, it moves to the right, it writes D at the location and then goes to the state R. So one easy way to remember is we will use smaller letters A, B, C, D, etc. for the tape alphabet, and something like Q, R, S, etc. for the state. So you write D here, right? But then the tape head is moving. So now that's why the D came here, and then you go to R, right? And under what condition? So now B could be anything, right? So for all B n gamma, or it could even be hash. So this could be the leftmost symbol, right? Now another example is, let's say, BQA. Now let's say the same thing, it writes D, it goes to the state R, but it moves left, not right, but it moves left, right? So the stop row is the same. In such a situation, so basically what happens is A is rewritten as D, and it moves left, so the tape head comes here, and B, again, it was earlier the tape head was on A, so B does not change, so B comes here, right? And here is an instance, for instance, where all the three entries are different, right? Okay, the B moved from one location to the other, but if you just look at the exact positions, all the three entries are different. So now here B cannot be hash because B moves, right? Now another thing is, if suppose B was hash, right, under the same circumstances, if B was the hash symbol, RDL and delta QA, and let's say so wait to write B, so let me just write hash, right? In such a case, it will try to move left, but it cannot move any further left, so it just becomes R and D, and the hash remains here, right? So this is some instances where so in all the three instances, all these three examples here, the state is in the top row, middle of the top row, right? And it is also there in the bottom, but again, bottom, it depends on what move it makes, but it's always there in the middle of the top row, right? Now maybe I'll just to illustrate, I'll just show one or two examples where it's in the right end of the top row. So let's say it was like this, BCQ, and let's say RDR was in the transition function. Okay, so what does it mean? It means now it is not A, sorry, for some symbol here, right? Suppose there is some symbol such that upon reading, so I am just denoting by star. Suppose there is some symbol star for which upon reading star and being at a state Q makes the tape head go to the right, and it overrides the whatever symbol with this new symbol D and goes to the state, enters the state R. So B will remain here, C will remain here, but this location was earlier something star, right? So this location was a star here. Now this star is being overwritten by D, right? And this Q will now point to, because the tape head is moving right, it will come here. So it's not Q now, the new state is R. But that doesn't matter because the 2/3 window, we just are interested in this, right? And here again, B could be anything. B could be gamma or hash, and C could be any symbol, right? Maybe I'll just do one more example. So let's say BCQ, and if R star L is in delta Q star, right? So again, this is a similar occurrence where it is reading star here. Upon reading this, it moves to the it moves to state R, and it moves left, right? So B is here, R comes here, and it moves left here. And now instead of the earlier star, maybe I'll just write this star with a hat or something, bar or something. So now we have this situation. Again, what is written in green does not really matter because at this point we are only focusing on the 2 by 3 window. So this is what we have. Again, this is just two instances of the state symbol being on the top right. So here Q, here Q. Again, we could make other windows where the tape symbol is in the top left, and we could also have other set of windows where there is no state symbol in the top row at all. So as I said earlier, one example could be A, B, C and A, B, C below. So it could remain unchanged, but it could also change because maybe the state is here. Let's say I just denoted by green here, Q, and now the Q decides to come in here. So this, instead of the C, now the tape head moves to the left. So such things are also possible. So again, in the 2 by 3 window sense, this is also possible. So I am just giving some examples of how the windows can be constructed. Anyway, the point is that all that we will do is to check these 2 by 3 windows. So what we will do is to check the entire table and check whether all the 2 by 3 windows are valid 2 by 3 windows. And there is a finite list of these valid 2 by 3 windows, because these 2 by 3 windows are only dependent on the Turing machine n and the transition function. So again, this is not the, whatever I drew is not the exact is not the exhaustive list of windows, but it is some list. And as I said, the number of windows is only dependent on the machine n, and it is not dependent on the input length. It's not dependent on the input, it's not dependent on its length. So it's a finite number. It may be a big number, but it's a constant, right? And the main point that we want to say is that if all the 2 by 3 windows are valid, then for each row I plus 1, it is a valid successor of the previous row I. Why is this true? It's very simple why this is true. Because if a symbol is not adjacent to any state, so let's say the state is at a certain location, maybe if let's say this is the state Q, and let's say this is X, this is Y, or whatever. Now if a state is here, let's say R, or maybe let me say A or something. Now A is not going to change because this is where the tape head is, over at Q. So if it is not adjacent to a state symbol, it will not change. And this is true because for all the windows which do not have the state symbol, the middle element is unchanged. So for instance, here there is no state symbol here, A, B, C, there is no state symbol in the top row. For all the valid such valid windows, the middle element remains unchanged across top and bottom. So if a symbol is not adjacent to the state, it is preserved from the first row and going to the second row. If a symbol is adjacent to the state symbol, okay, so something like X, Q, Y, where let's say X is some symbol, Y is some symbol, and Q is a state. Now what we can do is there will be a window where Q appears in the middle, and we are talking about X or Y which are adjacent to Q, and so the next row, this 2 by 3 window that comes like this will completely determine how what should follow X or what should follow Y. So if it is not adjacent to a state, then it is unchanged. If it is adjacent to a state, this window where the state appears in the top of the middle of the top row, that will fix what happens. So maybe upon reading Y, it writes D and then moves left to state, let's say R. So then this is what it is. So now the entire thing is captured by this window, right? So the entire window, this window captures the entire move. Hence it is enough to check only the 2 by 3 windows. So we do not need to check the entire row. It's only enough to narrow our focus to a 2 by 3 window, but we need to check all the 2 by 3 windows. So this is again a consequence of the fact that the computation in a Turing machine is extremely local. It happens only near the where the tape heads are. Okay, so now what is the point of or how do we benefit by focusing only on the 2 by 3 windows? That is because now again our goal was to write a formula for 5 move. Now we can write a formula for 5 move in the following way. You go through all the windows ij, right? Say sorry, 1 less than or equal to I, comma j less than or equal to n power k. It's a big AND followed by inside the AND we say ijth window is legal, which means the ijth window is legal. Now how do I check whether the ijth window is legal? Again it requires a Boolean formula. So we check, basically we just check that what is the ijth window. So ijth window means ijth 2 by 3 window. So again if this is a 2 by 3 window, this is cell ij. Okay, the top middle is considered to be the cell ij, right? We basically check that this window is one of the legal windows. So we check whether this window is, so let's say we have a list of 100 legal windows. We check whether this window is window 1, window 2, window 3 and so on up to window 100. So this OR, there is an OR function over all the 100 possible windows, and inside the OR function we are just checking something like this. We just check something like xi j minus 1 a1 and xi j a2 and xi j plus 1 a3 and xi plus 1 j minus 1 a4 xi plus 1 j a5 xi plus 1 j plus 1 a6, right? So basically we are just doing this, we are just checking whether the ij minus 1th entry is a1, ijth entry is a2, ij plus 1th entry is a3 and so on. Basically we are just checking whether the entries are what is given here, and we do that for all the valid windows and then OR over all the valid windows. This may seem like a big formula, right? We have a big AND over all the I comma j and we have a big OR over some constant number of things which are the number of valid windows, right? We want to show that it's a valid window and we have computed that. Now with this, right, we have shown a formula for 5 move which is a satisfiable formula, and with this we have shown that what we wanted to show, phi is in SAT if and only if n accepts W and n accepts W if and only if W is in A, because n is a decider for A, right, which is the main thing that we want to show. But remember that there are two things for a reduction. One is that W is in A if and only if f of W is in the other language, so in this case SAT, right. So in this case f of W is phi, and we also want that the construction of f of W is in polynomial time, right. So we also need to show that the construction of phi can be done in polynomial time. So let us see the sizes of the formula, right. So let's start with phi each of these parts. So phi is, let's start with phi cell, right, it's in polynomial time. So phi cell is a big AND, right, of over I comma j. So there is n power k times n power k, and inside this is of size delta, and this is maybe of size delta squared. But assuming that delta is a function of, since delta is a function of only the machine, it's not a function of the input length. So this is a constant size, right? Once I and j are fixed, this is a constant size. So phi cell is of size n power k times n power k times some delta or delta square, which is, again, this is independent of n. This is order n power 2k. Phi start, sorry, it is just checking the starting row. So this is of length exactly n power k. There is not even asymptotically. Then phi accept, it is just a big OR looking for the accept state. It is length n power 2k. And phi move, which we just saw now, not in the previous lecture, in this lecture itself, it is just number of valid windows, right, multiplied by n power 2k multiplied by 6. So number of valid windows over here, and each window has 6 entries multiplied by I and j, so which is of n power k each. So again, this is order n power 2k, right? This is order n power 2k. Hence, the entire construction, everything is polynomial in the input length n. Hence, the entire construction of phi, the resulting phi is of polynomial size. And the construction is also very straightforward because it's a very well structured formula. Right? Phi start and phi accept are easy to write. Phi move is also easy to write because you could have a loop to generate that. So in fact, the fact that we could write the formula phi move in such a crisp way itself indicates a program or an algorithm to write down, generate phi in a efficient manner. Hence, there is an easy algorithm to generate phi, and hence phi is constructible from W in polynomial time. This completes the proof that phi is constructible in polynomial time, and hence this is a polynomial time reduction of the language A to the language SAT, and hence, so we took an arbitrary language A, right? So the only property that we insisted on A was that it is in NP, and from this we reduced to SAT. This means any language that is in NP can be reduced to SAT in polynomial time, which means that SAT is an NP complete language. Okay, now I'll just conclude by a very short point that I'll make. So we showed that SAT is NP complete. What about 3SAT? So recall 3SAT was a 3CNF SAT formula, which means it is set of all it should be satisfiable, and it should be something like this. Let's say x1 or x2 complement or x3 complement and x1 or x4 or x5 and so on. So each clause has exactly 3 literals, right? And it is in the conjunctive normal form, which means it's an AND of clauses, and each AND is an OR of literals. So if we want to show 3SAT is NP complete, one way could be possibly to show that SAT reduces to 3SAT. Again, this is some of the properties that we saw earlier, that we could reduce NP complete, one NP complete language, if B reduces to C in polynomial time and C is known to be in NP and B is NP complete, then this would imply that 3 sat is NP complete as well, right? However, what is it turns out to be a bit easier. So we started with an arbitrary language here, right, in the proof that sat is NP complete, and then we reduced it to a Boolean formula. Now, if we can make the Boolean formula itself a 3CNF formula, keeping without changing the fact that this formula will be satisfiable if and only if the given string W is in A. If we can obtain that, right? If we can obtain that, then that would be even easier, right? So exactly similar type of proof, but then make sure somehow that the resulting formula is a 3CNF formula. So it's an AND of 4 things again, just to recall, right? It's an AND of 4 things. So that way is fine. So now if each of these 5 start, 5 move, 5 accept and 5 sell are 3CNF formula, the AND is also a 3CNF formula, right? Because it's an AND of these things. So let's look at 5 cell. It's an AND of some things, but this is not the 3CNF form now. Can we modify it? 5 start is just an AND of things, right? 5 accept is just an AND of things, right? In fact, I think there is an error here. This is actually wrong. Sorry for the error. It's actually should be OR. Right? I'll make the correction. I apologize for the mistake, and I'll make the correction when I circulate the notes. Right. Right. So none of this is again none of this is in the 3CNF form. But the point is we can modify it into 3CNF form. So the way to do it, maybe the simpler way to do it, the step-by-step way to do it is to first show that the formula generated can be a CNF formula, means it's just an AND of ORs, right? AND of clauses, and where each clause is an OR of literals, without really paying much regard for how many literals are there in each clause. And once that is done, you modify it into you somehow modify it into a formula where each clause has exactly 3 literals. So again, I've just written down these 2 things as questions. So show that each of these can be written in CNF form, and once something is in CNF form, we can modify it into an equivalent 3CNF form. I'd like you to think about these 2 problems. It's not that difficult. Just play around with Boolean formula and you may get it. Okay. With that, I'll conclude this lecture. Most of this lecture we just focused on 5 move, and then we summarize the rest of the proof. Okay. Thank you.